Hello. Let us start the next part of our nonlinear control system lecture series. So, in the last session, we had seen on phase plane, what is a phase plane and what are the different types of equilibrium points. Okay. Now, we will see a little more detail in on about phase plane method. Okay. So I will write down the common equation that we have been dealing with for the last 2 3 lectures. So it is x double dot plus 2 zeta omega n into x dot plus omega n squared into x equal to 0. Okay. So we know that we have been dealing with this equation. So we know that if x1 and x1 is equal to x and x2 equal to x dot are the phase variables, and if we represent it in a plane, x1 and x2 in a plane, we call it as a phase plane. Actually, x1 and x2 in a plane, we call it as a phase plane. Okay. Effectively, it is a graphical way of representing the values of x1 and x2 at different instants of time. Okay. So if I have an initial point, if you are given an initial point of x1 and x2, we will see where this equation is taking x1 and x2 in time. Okay. What will be the velocity and what will be the position of the vehicle, in fact, after some time. Okay. So this is an unforced system, so it has to, like, all the oscillations have to come to 0 if zeta is less than 1. Okay. So now this kind of a trajectory is for zeta less than 1 for some initial condition, and this, the path or curve traced by the phase variables on the phase plane is called a phase trajectory. Okay, this we had seen in the last lecture. So if I take some other initial point and if I try to trace a path, it will be something like this. Okay, it will, since zeta is less than 1 for this kind of equation, it will be like a stable focus, right? It will be something of the sort. Okay, and if I take some other initial point, I will also move. If I take some initial point here, it also moves like this and it comes back to here. Okay, in the last class, we saw that none of these trajectories will intersect. Okay, are intersecting. So that is why I have drawn it like that. Okay, so now if I start plotting all the possible curves starting from the with different initial conditions on this plane, what all possible curves initial conditions are there, I'll take all the possible initial conditions and I will plot all the curves on this plane for zeta less than 1. Then that kind of a plot is called a phase portrait. Okay, then that is called as a phase portrait. So I will write it as phase trajectory. This is a phase trajectory. And if I plot, or the family of all the possible curves for different initial conditions is called a phase portrait. Okay, so phase portrait is the family of all possible curves. Okay, of all possible curves with different initial conditions. Initial conditions. Okay, now if you look at this system, we can see that if we can plot for zeta equal to 0, zeta greater than 0, so this phase plane analysis, if you are able to draw this curve like this for any system, if you are able to draw this curve, then we get a physical we get an intuition on what kind of a system is this, like whether, what kind of a system. We can draw this for nonlinear systems also. So what kind of a system, or what is the response of the system. So that is the advantage of this phase plane method. In fact, it is a graphical method which gives us an intuition about what the system response would be. Like, so if it was a circular path, we can say that it is an oscillatory system. If it was we can say whether it is an overdamped, underdamped, and all these kinds of, or whether system is stable or not. Okay. And usually these kinds of this float is restricted for second order systems. Okay, I think I have discussed this in the last class. If we are having a third order system, actually if this is x1 and x2 plane, x1 x2 plane, and if I have a third dimension also, if I take the third plane also, sorry, a third axis also, what we do is we have to project the system onto each plane and then see the look at the characteristics of the system. This becomes more complex, so usually it is restricted for second order systems. And then if you the next condition is the next characteristics of a phase plane method is it is plotted usually for second order system with constant parameters and constant or zero input. Actually, if you look at this equation, the parameters here, these are the parameters of the system. 2 zeta omega n and omega n are the parameters of the system. These values for these systems are not varying with respect to time. So if these are not for a linear time invariant system, for linear time if I write here, for a linear time invariant system, the parameters does not vary, right? Parameters does not vary with time. Doesn't vary with time. For those kinds of systems, the plotting becomes plotting is vary with time. Plotting is easier because the trajectories will not intersect each other for a linear time invariant system. Since the parameters does not change with time, the trajectories will never intersect. The only point at which they intersect would be the equilibrium point. Intersect means they will meet, would be the equilibrium point for a stable system. For an unstable system, they will start from the equilibrium point. They will start together from this point and converge to infinity and diverge to infinity. But if it is if the parameters are changing with time, what happens? There are the trajectories may intersect at some point of time, and it becomes a tedious task for uh, plotting all these trajectories in time. So we will be considering systems with constant parameters, and also if the system is having a zero input and or a constant input. These conditions are imposed on whatever we are going to do, because for the systems which does not follow these conditions, the trajectories may intersect at different points, so it becomes complex. Okay. So now we will go and see a little bit more on phase portrait. Okay. So we will see. Anyway, we have seen the phase trajectories for different systems, and today we have seen in MATLAB also the phase trajectories for different systems. And now we should know how to plot all these things. If we are given a system, we should know how to plot it. Okay, so there are two ways of plotting the trajectory of a system. One is the analytical method of plotting, and other one is a graphical method. In graphical method, we have to learn two more things. One is Isocline method, and the other one is delta method. So we will see this this and this in three different lectures. Okay, in that we will deal with that in the coming lectures. Okay, now we will go and see get a little more better idea on this phase plane method. Okay, so now we have the system. I will write it as x dot general system. If I write it as x dot is equal to f of x, if I have written x as bold letters, that means it is a vector. So x means x is a function, x is a vector with phase variables x1 and x2. So if x is represented like this anywhere throughout the lectures, that means it is a vector. Okay. So just for notational convenience, I have given that. So here, we know that x1 is equal to x2 for the previous system, and x1 dot is equal to x2 for the previous system, which we had seen here. And maybe I will write it once again: x double dot plus 2 zeta omega n into x dot plus omega n squared, omega n squared into x equal to 0. So we had chosen x1 is equal to x and x2 is equal to x dot. Therefore, x1 dot is equal to x2 and x2 dot is equal to minus 2 zeta omega n into x1, x2 minus omega n squared into x1. Okay, this is the equation for these are the state equations for the system. So I can write this as a function f1 of x1 comma x2, and this also as a function of x1 comma x2. These are f1, and we have represented it in this form. So now let me draw the phase plot here. Okay, this is a phase plane. Okay, so I have x1 here and x2 here. Okay, so now how do we, for example, if I am having some curve on this plane, and you are given a differential equation representing this curve, how will you plot this curve given an initial condition? What we usually do is, if this is the plot that we have and we don't know this curve, actually we don't know this curve, assume that we don't know this curve. Okay, I will rub it off. I will draw a dotted line, and we don't know the exact curve, what this curve is exactly. We only know the differential equation representing this curve. Okay, this is not the differential equation representing this curve. I have just simply drawn a line here. How do we plot this curve? What we usually do is, if you are given an initial condition, suppose you are given the initial condition that is here, that is x1 and x2 is given initial condition, that is I is given as x10 and x20 are the initial conditions of the system. Sorry. So if you look at this curve, we can see that if you take a tangent along this point, at every point on this curve, if I draw a tangent, it is effectively the slope of this curve at every point. If I try to draw the slopes of this curve at different instances of this curve, what we will get? We can effectively get the path of this curve. So what we usually do is, we take the curves, we mark the slopes of the system at different points. Okay, on at different points in space. So if initially, if you are given a point here x10 as if you are given an initial point here, first what you do is you plot, you find out the slope at this point. What is the slope at this point? It will be dx2 by dx1 is the slope, and it is substituted at xi0 and x20 at I. So we will get the slope at this point, and we will move in the direction of the slope from I to a little bit further, and we will reach some other point here, because if we can move in the direction of the slope, we will reach this point. And so we have got the next point. If this is I0, I have got the next point I1. From I1, I will find out the slope. Again at I1, we will find out the slope as dx2 by dx1. We will find out the slope at I1. And at I1, I will again find out the slope. Okay, I will find out the slope, and I will move along the slope to another point I2. So I will get I2. Like that, I can trace the whole path. This is how we trace the path for any function on any plane. So similarly, in the phase plane also, if you are given some equation, I can plot the trajectory for that equation if the slope at every point on the system is given. So what we can usually do is, on every point wherever we have space, we'll take this point, every point we'll consider infinite many points on this space. For I will draw some points on the space, and let zeta equal to 0 for the system. So we will try to form the slopes at the points defined in space. So what we do is, we get at this point we can find out the slope because we know the value of x1 and x2. We know the value of x1 and x2, and I can find out the slope. What is the slope here? X dx2 by dx1. What is dx2 by dx1? It is f2 of x1 comma x2 divided by f1 of x1 comma x2, right? So that is the slope. So what is that value? It is f2 of x1 comma x2 is minus 2 zeta omega n into x2 minus omega n squared into x1. F1 of x1 comma x2 is x2. So at this point, for example, if this point is 1 and this point is 2, so what you will do at this point, you substitute this equation, that is minus 2 zeta omega n into 2 minus omega n squared into x1 is 1 divided by, what is this, f1, x2 is 2. So if zeta and omega n is known, here zeta is equal to 0. So it becomes minus omega n squared by 2. So for this, at this point, what will be the slope? It will be minus omega n squared by 2. So similarly, we can plot the slopes at every point in the space of the phase plane. So I can plot here, I can plot here, I can plot here. I will get as many slopes as possible. I can plot as many slopes as possible in the phase plane. Okay, so everywhere I can plot. Okay, if I am having all these uh, slopes, if I know I am able to compute all these slopes in space, then what is the difficulty in finding or in finding out the phase trajectory or drawing the phase trajectory? Only thing is, we have to we should have an initial point. Now if you have an initial point here, I know I have to go down here. If I go down here, I know I have to go trace this path. So similarly, I will go like this, like this, like this, like this, like this, like this, and I will come here. This is how we plot the phase trajectory. This is the idea of plotting the phase trajectory. So in space, we can see infinite, any number of slopes, that is arrows, shows the slopes at every point in space. Okay, so we had seen in MATLAB these arrows. So we will also see some of the characteristics of these slopes in space. Okay, we'll see two characteristics of these slopes in space or in the phase plane. Okay, so now uh, so the first characteristic is the state trajectory crosses the real axis at 90 degree. We'll see why. So it is saying that this is the real axis. Sorry, actually it is not the real axis. Crosses the x1 axis. Actually, I did it wrong. Uh, x-axis, x1 axis, x1 axis at 90 degrees. Okay, at 90 degrees. So it is saying that all the phase trajectories will cross it at 90 degrees. We'll see why. So we will try to find out the slope at this point. So what is the slope? dx2 by dx1. So what is x1 here? X1 dot is equal to, always equal to x2. This is how we have represented the phase variables. So whatever value we have on in the numerator, the denominator would be x2. The denominator would be x2, right? Since the denominator is x2, what is x2 on this x1 axis? The value of x2 on the x1 axis is 0. So it is numerator divided by 0, right? Numerator divided by 0, which is equal to infinity. Since it is infinity, what will be the value of the angle? So tan inverse of infinity is 90 degree. So this is clear, right? So on the x1 axis, wherever we go through the x1 axis, we can see that the trajectory crosses the x1 axis at 90 degrees. Okay, here it will be downwards, but here it will be upwards. Okay, so here this is how the trajectory crosses the x1 axis. Another important point about the phase trajectories is that the state point moves from left to right on the upper half of the real axis and from right to left on the lower half of the real axis. So I will explain it. So we have the state equation. So I'll just go to the state equation. This equation, x1 dot is equal to x2. This equation is important. X1 dot is equal to x2. So we will consider this equation alone. This whichever system we are considering, we usually try to represent it in this form. So for all the systems where we represent it in this form, we can write it as x1 dot equal to x2, which implies the change in x1 with respect to time is equal to x2. Okay, if x2 is positive, if x2 is a positive value, x2 is a positive value, that means that the change in x1 is positive. That means if change is positive, and if x2 is negative, the change is negative. Change in x1 is negative. Change in x1 is negative. Okay, that means if I am having, so in the x1, x2 plane, if you look at the x1, x2 plane, in the upper half, this is the upper half. I will draw this as the upper half. This is the upper half. In the upper half, the values of all the x2s are positive. In the lower half, if you look at the lower half, the values of all the x2s are negative. x2 is negative. x2 negative, and here x2 is positive. Positive. So if what will be if I consider a point here in the upper half, what is this equation saying? The change in x1, if x2 is positive, if I consider a point here, at this point x2 is positive, I have got a positive value of x2. So the change in x1 is positive at this point then. That means x1 is increasing at this point. So x1 can, like the slope, if I try to draw a slope, I should draw it in such a way that the value of x1 should increase. If I want to, suppose I am here at -3, if I want to increase x1, I have to move towards maybe -1 or -2 or something like that. Okay, if x2 is 2, that means I have to move towards -1. That means the slope should move towards -1. This is, if this is -1, if x2 is 2, if x2 is equal to 2 at this point, if x2 is 2 at this point, the slope should go to -1. I can go like this also -1. I can reach it in different ways. I can go like this also -1, this way also -1. In any way, I can reach -1 at this point. Okay, these are the different slopes that I can draw it from this point, so that the value of x1 increases. Okay, value of x1 increases. So if I want to increase the value of x1, the trajectory has to move from left to right. Then only I can increase the value of x1. Similarly, if I go to the lower part, here, if I am here, somewhere here on the lower part, here I am at minus 3, assume I am at minus 3, then what happens? What is it saying? What is this equation saying? The x2 at this point is negative. Let it be minus 4, minus 2. Let it be minus 2 at this point. So what is it saying? That means dx1 by dt at this point is minus 2. That means x1 has to decrease. If x1 has to decrease, then the slope should have to be like this. x1 has to decrease by 2 values. That means it has to go to minus 5. So x1 has to decrease by minus 2. So if this is minus 3, it has to go to minus 5. So it can go to minus 5 in different ways. This is at this point, this is one way of going to minus 5. I can have a different slope and go to minus 5. I can take this slope also, I can go. In this way also I can go. This way also I can go. Different ways I can reach minus 5, right? These are the different slopes I can draw at this. This is not a perfect slope. I can move to minus 5. Okay. So what does these slopes say? That means whatever slope I draw at the lower half of the x-axis, it says that the change, the state point, that means the straight trajectory moves from right to left. That means the lower half of the x1 axis, the state trajectory moves from right to left, showing there is a decrease in x1, in the value of x1. So there is some mistake, small mistake here. I have written it as real axis, which came to my mind like that, x1, because we have been dealing a lot with real axis for wrong. So it is x1 axis. Okay, that's it. So that's about today's session. So I will conclude by showing one or two face portraits. So this is face portrait that we had seen in MATLAB. So this is for this kind of a system for zeta equal to 0. So we can see that there is oscillation. So throughout we can see the red lines, all these red lines. What does this red lines show? These red lines show the slopes at every point in the x1, x2 axis. If you look at the slopes itself, we can see that the trajectory is going round and round, right? So wherever, if I want to start from this point, I can start here. I can start here, follow this trajectory, and then I can follow this path, and then I can see that I am coming like this. Okay, actually it didn't come out well. Something like this. Okay, I can follow this path and okay, and get a circle like this. So now, and another point that we had seen is, if you look at on the x-axis, we can see that all the trajectories are crossing it at 90 degrees. All the trajectories are crossing it at 90 degrees. Actually, I had drawn the x-axis a little bit at the bottom of this line. Somewhere, some small mistake is there here. So actually, it will cross at 90 degrees. All the trajectories which cross it will cross at 90 degrees. Okay. Here also we can see that all the trajectories are trying to cross it at 90 degrees, and all the state points on the upper half are moving from left to right. See, here also it is moving from left to right. Wherever we take, it is moving from left to right. Here everything is moving. At the bottom half is moving from right to left. See, there is a decrease here in x. Here there is an increase in x. Okay. So this is it. So if you look at the if you look at the slopes itself, we get an idea what is happening in the system. See, it is something which is converging, right? It is having a heavy damping here. It is converging. See. And if you go to the next figure, this is for zeta less than 1. Here also, it is showing some kind of an oscillation here. So it is showing some kind of an oscillation here. So that is why it is going like this. Okay. And the last picture is for the limit cycle here. And for the limit cycle here, we can see that here, if I have, this is for the stable limit cycle I have shown here. And for mu greater than 0, So if I choose, that means I have a flexibility in choosing the x if the limit cycle is a stable one. That is the only advantage of this limit cycle. Otherwise, these limit cycles are undesirable for any control systems. That means if the amplitude, that means here we are having a lower amplitude, so it is not of much of a problem. So if we are having a system which is oscillating with a very high amplitude, we cannot like work with that system. So that is why the system limit cycles are undesirable for control systems. But if the amplitudes, if the oscillation amplitudes are lower, then we can even work with systems with stable limit cycle, because even if I change the value of x, that means if the x is if I choose an x, if I choose a lower value of x also, I can reach the limit cycle. And if I choose a very high value of x also, what happens is that I will the system will converge and reach to that limit cycle. So that's it. So here also we can see in this picture also we can see that all the state points are moving from left to right. Here it looks like it is going upwards, but if you look closely we can see that there, if I move from this point to this point, the difference, if I take the difference between this point and this point, effectively the value of x1 is decreasing. So from right to left. Here also it is moving from left to right. So even if it is small, if this height is going like this very steep, so that is why we feel it feels like it is going downwards. So actually what is happening is, it is actually the value of x1 is increasing here, but to a very small level. It is increasing at every point of time. So that's about phase portraits. So now we in the next lectures we will see how to construct phase portraits. Okay, we will see the method. We will see the analytical method for construction of phase portraits. Okay, thank you. I'll stop this.